Hi friends, now we will have a tutorial session and we will solve some numerical problems on the basis of our discussion held in the last 4 classes. The statement of the first problem is calculate the theoretically power available from a flow of 1 meter cube per second water with a fall of 100 meter. Due to energy loss, the practically available power will be less than the theoretically available power. If the efficiency is 80%, then calculate the actual power that can be obtained. So, this is the problem statement. So, as you know, this is the problem of a hydro power plant based on the hydro power plant, and we know the energy equation of hydro power plant. So, we will use that energy equation so that we can get the theoretically available energy in the water, and then if we multiply it by the efficiency, we will get the actually available energy. So, we know that the theoretically power available from falling water, that can be calculated by this formula, that P TH theoretically available power in watt, that is equal to rho into cube, that is the water flow volumetric flow rate, that is meter cube per second, and G is the acceleration due to gravity, and H is the falling height. So, that is mgh, like so the m is replaced by q into rho. So, this is the expression we have discussed in our previous class, and now we have the data of rho, we have the data of q, we have the data of g, and we have the data for h. So, in this case rho is equal to, say, we can assume that is equal to 1000 kg per meter cube for water, and q is given 1 meter cube per second. So, 1 meter cube per second, and then g is 9.81 meter per second square, and h is nothing but 100 meter, which is given here. So, we will put this in this expression and we will calculate the value of PTH, and it is coming as 1000 into 1 into 9.81 into 100, that is equal to 981,000 watt or 981 kilowatt. So, this is the theoretically available energy. Now, practically available energy, we have to multiply it by efficiency of the system with the PTH. So, mu rho q g h. So, we will put it here, and as the efficiency given is equal to 80%. So, 0.80 into this much 981 kilowatt. So, we are getting 784.8 kilowatt. So, this is the practically available energy. So, problem number 1 we have solved. Now, we are moving to problem number 2. The statement is a turbine develops 9000 kilowatt when running at a speed of 140 rpm and under a head of 30 meter. Determine the specific speed. So, this is a again problem related to hydro turbines, and here we have to define the specific speed. So, specific speed is nothing but the speed which is equivalent to a turbine having the same size, and that turbine which can produce unit power by using unit head. As you have discussed in the previous class, that Ns, the specific speed, is can be related with the speed of the turbine, the power rating of the turbine, and the heat available. So, N into root P by h to the power 5 by 4. Now, if P and H both are 1, then Ns is equal to N. Ns is equal to N when P and H both are 1. So, this is the definition of Ns, and if we put, in this case we will put the P and the H value provided in the statement, N value is also given to the statement, and we will calculate the Ns value. Now, what is the value of N? That is the turbine speed or the rotation of the rotor or the turbine shaft, that is equal to 140 rpm as given here, and then P power rating is given also 9000 kilowatt. So, it is shaft power is 9000 kilowatt, and then head is 30 meter. So, it is 30 meter. So, we will be putting this value here. So, 140 into 9000 to the power half, that is power rating to the power half, and divided by 30 to the power 5 by 4. So, this, and we are getting that 189.16 rpm. So, 189.16 rpm is the specific speed of that turbine. Now, let us move to problem number 3. So, it says for a typical small hydro system, water flows through a head of 2.5 meters and a turbine that could take a maximum flow rate of 3 meter cube per second. If the turbine efficiency would be 85%, drive efficiency 95% and generator efficiency 93%, then calculate the actual power generated in hydro plant. Again a problem based on hydropower plant, and in this case efficiency, different types of efficiency has been, that is the turbine efficiency 85% and efficiency of drive is equal to 95% and efficiency generator 93%. So, these are the efficiencies. So, we will be getting the overall efficiency multiplying by these 3, 0.85 into 0.95 into 0.93. So, that is the overall efficiency for the energy conversion, and then we will use the energy expression and we will get how much energy is available. So, now the turbine efficiency is given 85%, drive 95%, generator efficiency 93%. So, we will by multiplying of this we are getting 0.751 or 75.1% overall efficiency. So, then we will use the energy expression. So, here head is equal to 2.5 meters, flow is equal to 3 meter cube per second, and then the maximum power output of the system, that can be theoretically maximum power which can be available, that is equal to PTH, that is equal to rho into Q into G into H. So, we will be putting the rho value 1000 and Q is 3 meter cube per second. So, 3 and 9.81 G and H is 2.5. So, we are getting 73575 watt, that is equal to 73.575 kilowatt. So, then what will be the practically available power? So, we have to multiply it by efficiency. Overall efficiency we have got there is equal to 0.751. So, this 0.751 into 73.575, that is equal to 55.254 kilowatt. Now, the problem is solved. We are coming to the next problem, problem number 4, and which says the tidal range of a bay could approach 17 meter in extremity. About 110 billion tons of water flow into and out of the bay in one cycle. Calculate the total potential tidal energy of the bay in this extreme case in 1 year by using bidirectional turbines. Gravity of acceleration 9.8 meter per second square. So, this is a problem based on the hydro turbines, but water level is generated due to the tides. So, tidal energy in fact. So, here we have 70 sea level, if we have, then it will be during high tide water will go towards the river directions and we will be having some water head, we will be having some water head here. So, this water head maximum is equal to 17 meter, and it is also given that 100 billion tons of water flow into and out of the bay in one cycle. If this is our bay, so it is one cycle it is going out, and again low tides it is, this is going in, high tide and low tide it is going out. So, both the cases, if we install one turbine, so if we install one turbine here, so it will be able to generate electricity as the turbine is bidirectional, it is given. So, we will be using here also the energy expression for the calculation of the available energy and which can be converted. So, now again it is told that we have to calculate on yearly basis. So, in a year how many times of tides we will get, that we have to calculate, because one tide is the source of the availability of the heat. So, that is why we will be calculating number of tide cycles, per year. So, that is equal to, so we have 365 days into 24 hour total hour and divided by 12.4 hour, at 12.4 hour is required for one tide. So, one cycle we are getting total 706.5 cycles in a year. So, the number of times of the tide to drive turbines, for once we are getting 2 movement of the turbines in opposite direction. So, number of times for the tide to drive the turbines is 2 into n cycles per year, that is n CBC, that is equal to 2 into 706.5. So, 13. So, 1413, 13 times a turbine will run. Then what will be the tidal energy? Here mgh into n divided by 2. Why so? This is the potential energy which is stored here, this region, this bay, that will provide the electricity through the conversion in the turbine. So, potential energy is converted to kinetic energy of the water, then it is mechanical energy of the shaft, and then through the generator it will give electricity. So, in case of hydro turbines, which we had used that energy expression is equal to mgh, but here mgh by 2, because this height will not be constant, this height which is the maximum height h which will not be constant, it will be maximum initially, then again it will be reducing and come to 0, and on the other hand, on the other case it will be 0 and gradually it will increase. So, that way, so this will be divided by 2, average is taken. So, mgh into number of times the turbine is operated. So, that n into mgh by 2, that will be the energy potential for this turbine. So, total tidal energy per year is equal to n into mgh divided by 2. So, here n is equal to 2 nc, that is equal to 1413. So, we will be putting here 1413, and m equal to what? M is equal to, it is told that 110 billion tons of water. So, 11 means 110 into 10 to the power 12 kg of water. So, we can write it here 1.10 into 10 to the power 14 kg of water. So, this 1.1 into 10 to the power 14 kg of water we are getting, and g is equal to 9.8 meter per second square already given, and then height is equal to 17 meter maximum height. So, that will be divided by 2. So, we are getting here this much of energy which is available throughout the year. So, that will be equal to 1.3 into 10 to the power 19 joule, or 1 joule if we want to convert it into kilowatt hour, then we can use this expression that 1 joule is equal to 2.77 into 10 to the power minus 7 kilowatt hour. So, if we use this conversion in terms of kilowatt hour, that this joule will be converted to 3.6 into 10 to the power 12 kilowatt hour. So, this is the energy which is generated throughout the year. So, our problem was, we were asked to calculate the total potential tidal energy of the bay in this extreme case in 1 year by using bidirectional turbines. So, this is this much of energy we can produce in a year by using bidirectional turbines in this extreme case. Now, the problem is solved and we are coming to next problem. So, problem number 5. So, this says, if the tidal range of the tide at particular place is 10 meter, calculate the potential energy content of the water in the basin at high tide if the tidal power plant has surface area of 9 kilometer square. Assume surface density of sea water to be 1025.18 kg per meter cube. So, this is again a tidal energy problem, and it is asked to calculate the potential energy content of the water in the basin at high tide if the tidal power plant has surface area of 9 kilometer square. So, in this case what will be the energy content that we see? The energy content, potential energy contained in a volume of water, that is equal to half into A into rho into G into H square. So, here we have one surface area, say so, say water is going this direction and we have this surface area that is equal to 9 kilometer square surface area. So, 9 kilometer square surface this way. So, then what will be the height of it? That will be the volume. So, A into H, that is the volume, into rho, this is the mass. So, that is equal to mass, A into H into rho. Then if I want to use the formula mgh, so mgh equal to A into H into rho, that is m, A into H into rho into G into H by 2, H by 2. This height is, the water height is not fixed here. So, H by 2 it is mentioned. So, H by 2 we are taking the average height. So, half m, so that is half into A into rho into G into H square, that is the energy potential of the tidal barrage. So, in this case H is the vertical tidal range and A is the horizontal area of the barrage basin, just to have discussed, this is our A, horizontal area, and then rho is the density of the sea water. So, density of the sea water normally varies from 1021 to 1030 kg per cubic meter. So, you can assume any value in between these two. So, the average one is taken 1025 kg per cubic meter, and G is the acceleration due to the gravity of earth, that we know that 9.81 meter per second square. Then as I just discussed, the factor half is due to the fact that as the basin flows empty through the turbines, the hydraulic over the dam reduces. The maximum head is only available at the moment of low water, assuming the high water level is still present in the basin. So, that is why the half is considered. So, in this case total range of tide is 10 meter, and then the surface of the tidal energy harnessing plant is equal to 9 kilometer square, and specific density of seawater is 1025.18 kg per meter cube. So, we will be putting these values in our energy expression. So, mass of the water equal to volume of water into specific gravity, that we know. So, mass volume of water mean area into tidal range of water into density of the sea water. So, 9 into 10 to the power 6 meter square. So, 9 kilometer square. So, that is converted to meter square. So, 9 into 10 to the power 6 meter square, and then tidal range 10 meter and is 1025.18 kg per meter cube is the density of the sea water. So, by the multiplication of these three terms we are getting here 92 into 10 to the power 9 kg. So, this is the mass of the water, and then potential energy content of the water in the basin at high tide will be half into area into density into gravitational acceleration into tidal range square. So, half into this area into this is equal to mass basically, and G and H square. So, we are getting 4.5 into 10 to the power 12 joule. So, now we have solved the problems, and total 5 problems are solved on the basis of our discussion held in the last 4 classes. So, thank you very much for your patience.